Hello, in this lecture we'll answer on two questions. In the first question, we find out the length of line segment DE that is equal to x. In the second question, we will find out the value of the shaded area that is inside the quarter circle. We'll start with the first question. In the drawing, we have triangle ABC. This angle ABC equals to 30 degrees. This angle ACB also equals to 30 degrees. And this angle DEE equals to 60 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units, and our mission is to find out the value of line segment DE that is equal to x. Okay, so we will focus on triangle ABC. In triangle ABC, those two angles are equal to each other, they are both equal to 30 degrees. So I will write it down. So this angle ABC equals to this angle, this is angle ACB. Both angles are equal to 30 degrees, therefore they are equal to each other. Okay, I'll repeat again. In triangle ABC, angle ABC equals to angle ACB. They are both equal to 30 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So here, in front of this angle, we have side AB, and in front of this angle, we have side AC. And according to the rule that I mentioned, side AB must be equal to side AC. Okay. Side AB equals to side AC. Okay, so I can write here that this side AC equals to this side AB. Okay, so in the next step, we will define angle BAD, this angle as alpha, and we will define angle EAD, this angle as beta. And we know that the sum of the angles in any triangle is equal to 180 degrees. And especially the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have in triangle ABC? This angle equals to 30 degrees plus this angle that is also equal to 30 degrees plus this angle that is equal to alpha according to our definition plus this angle that is equal to 60 degrees according to what is given as an equation plus this angle that is equal to beta. In total, the sum of those two angles, the sum of those all angles must be equal to 180 degrees. Okay, so So this expression expresses the fact that the sum of the angles in triangle ABC is equal to 180 degrees. So here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. 120 degrees plus alpha plus beta, in total they equal to 180 degrees. So here we subtract 120 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 120 degrees is equal to 60 degrees. Okay, so found out that alpha plus beta equals to 60 degrees. In the next step, we will do two constructions. In the first construction, from point A, we will draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. So here this angle equals to alpha according to our construction. And the second construction that we will do is from point C, we will draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. Okay, so actually this angle equals to 30 degrees according to our construction. In the next step, we will extend the two straight lines until they intersect with each other. And we will define the intersection point between the straight lines as point F. Point F is the intersection point between those two straight lines, in the extended two straight lines. So here we created triangle AFC. So in the next step, we will prove that this triangle AFC is congruent to this triangle ABD. Okay, or triangle ABD, this triangle is congruent to triangle AFC. So why those two triangles congruent to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So this angle BAD, is equal to this angle that is actually angle CAF, and they are both equal to alpha, therefore they are equal to each other. I will repeat again. Angle BAD equals to angle CAF, and they are both equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. Okay, here we proved that side AB equals to side AC. So we can write it down. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So this angle ABD, is equal to this angle that is actually angle ACF, and they are both equal to 30 degrees, therefore they are equal to each other. I'll repeat again. Angle ABD equals to angle ACF, they are both equal to 30 degrees, therefore they are equal to each other. So we actually proved that this triangle ABD is congruent. This is the sign of congruent to triangle AFC. According to angle side angle rule. I'll explain what I mean. We actually proved that those two angles and the side that attach to those two angles in triangle ABD are corresponding congruent to those two angles, and the side that attach to those two angles in triangle AFC. Therefore, we proved that those two triangles congruent to each other according to angle side angle rule. And from the fact that those two triangles congruent to each other, we conclude two things. First of all, we conclude that side BD equals to side FC. Side BD equals to side FC. Side BD of triangle ABD equals to side FC of triangle AFC, according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given us in the question, side BD equals to 5 units. So we can write here that BD equals to 5 units. And from this equation, 5 equals to BD equals to FC, we will derive that side FC is also equals to 5 units. Okay, side FC also equals to 5 units. So we can write here that FC equals to 5 units. And the second thing that we conclude from the fact that those two triangles congruent to each other is that side AD in triangle ABD is equal to side AF in triangle AFC. Okay, side AD is equal to side AF. Side AD in triangle ABD equals to side AF in triangle AFC. So, if we define side AD as A, side AD equals to A according to our definition. So we can write down that side AD equals to A according to our definition. Then, from this equation, A equals to AD equals to AF, we will derive that side AF is also equals to A. Side AF equals to A. According, okay. In the next step, we're join points E and F together by a straight line. And we will prove that the green triangle ADE is congruent to the orange triangle AEF. Okay. But before that, we've already proved that alpha plus beta equals to 60 degrees, therefore here this angle alpha plus beta equals to 60 degrees. So in the next step we will prove that the green triangle is congruent to the orange triangle. So we actually prove that the green triangle ADE is congruent to the orange triangle AEF. So why those two triangles congruent to each other? First of all, we just right now proved that side AD equals to side AF, so I can write down that AD equals to AF equals to A. I'll repeat again. Side AD in the green triangle is equal to side AF in the orange triangle. They are both equal to A, therefore they are equal to each other. In addition, those two sides, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So here this angle DAE, is equal to this angle that is actually angle EAF. They are both equal to 60 degrees, therefore they are equal to each other. I repeat again. Angle DAE in the green triangle is equal to angle EAF in the orange triangle. They are both equal to 60 degrees, therefore they are equal to each other. And finally, we have side AE, that is a common side. It belongs both to the green triangle and also to the orange triangle. So side AE equals to itself. It's a common side that belongs to both triangles. Repeat again. Side AE equals to itself is a common side that belongs to both triangles. So we actually proved that the green triangle ADE is congruent to the orange triangle, triangle AEF, according to side angle side rule. Repeat again, triangle ADE congruent, the green triangle congruent to triangle AEF, the orange triangle, according to side angle side rule. I'll explain what I mean. Actually, those two sides and the angle that is included between those two sides in the green triangle are corresponding congruent to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, those two triangles congruent to each other according to angle side angle rule. And from the fact that those two triangles congruent to each other, we will conclude that side DE equals to side EF. I'll repeat again. We'll conclude that side DE in the green triangle is congruent to side EF in the orange triangle, according to the same rule that corresponding sides in congruent triangles are equal to each other. But according to what is given us in the question, side DE equals to x. So we can argue that DE equals to x. And from this equation, x equals to DE equals to EF, we will derive that side EF is also equals to x. Side EF in the orange triangle is also equals to x. Okay? In the next step, I will present to you the law of cosines and we will implement the law of cosines in this triangle, triangle EFC. I've already mentioned the law of cosines a couple of times, so I will repeat on it shortly. So actually, the law of cosines is true in any triangle. So we write down that in any triangle, so actually if we have here triangle ABC that could be any triangle, this is triangle ABC. And we know that side AB of triangle ABC equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. And side BC equals to C units in its length. Then the following equation is true for triangle ABC. That could be any triangle. That C squared equals to a square plus b square minus 2 times a times b times cosine theta. I'll repeat again, in this triangle ABC, c square equals to a square plus b square minus 2 times a times b times cosine theta. So we will implement the law of cosine, this law, in this triangle FEC. So copy the triangle in this page and we will implement the law of cosine in this triangle FEC. This angle ECF equals to 30 degrees plus 30 degrees, that is 60 degrees. So this is triangle FEC that I copied from the original drawing. Side EF equals to x, side EC equals to 4, and side FC equals to 5. So according to the law of cosines, we implement the law of cosines in triangle FC, so we get here that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I repeat again, in triangle EFC, according to the law of cosines, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So we found out that x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, times cosine 60 degrees. Cosine 60 degrees equals to 1/2, so we substitute cosine 60 degrees by 1/2. So in total, this expression equals to minus 40 times 1/2. So here we found out that x squared equals to 16 plus 25 is 41. Minus 40 over 2 is minus 20. So we found out that x squared equals to 41 minus 20 is 21. So x squared equals to 21. Here we take a root out of this equation and we get that x equals to the positive square root of 21, or in terms of numbers it is equal to 4.58 units. And the reason that x equals to only the positive root of 21 is because of the fact that x is a length, and the length must be a positive number, therefore x equals to the positive root of 21, or in terms of numbers it is equal to 4.58 units. So the answer to the question is that line segment DE that is equal to x. It is equal to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay, so we finished with the first question. In the next step I will present to you the second question. So in the drawing we have a quarter circle. Inside this quarter circle we have a circle and a semicircle that are tangent to each other at this point. This circle is also tangent to the quarter circle at this point. And we know that the radii of each shape, that is to say the circle and the semicircle, is equal to 2 units, and our mission is to find out the value of this shade, the value of the shaded area. Okay, so first of all, because of the fact that this is a quarter circle, it means that this point is the center of the quarter circle. So we define this point as point O, and point O is the center of the quarter circle. And also this angle, it is a right angle, it is equal to 90 degrees. We'll define this point as point A. We'll define this point as point B. And we also know that because of the fact that this is a quarter circle, line segment AO and line segment OB, they are both the radii of this quarter circle. Okay, so this line segment AO and also line segment OB, they are both the radii of this quarter circle. So we will define the radii of this quarter circle as capital R, and therefore AO will be equal to capital R, and OB will be also equal to capital R. They are both the radii of this quarter circle. Okay. I will write here down that capital R is the radii, is the radius of the quarter circle. I repeat again, capital R is the radius of the quarter circle according to our definition. So here we have the radius BO of the quarter circle, or we can also say the tangent BO is tangent to this circle at this point. This is the point of tendency, so we'll define this point as point M. And point M is the point of tendency. Point of tangency of tangent OB with this circle. Okay, and we also have rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have tangent AB is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB in this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So we actually can implement rule number 1 in our drawing. First of all, we will define the center of this circle as point P, and we will define the center of the semicircle as point Q. So here, point P is the center of the circle, point M is the point of the circle itself, therefore PM is the radius of this circle, and the radius PM, this radius PM, it is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent OB in this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius PM. So if OB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. In the next step, from the center of this circle that is actually point P, we will draw perpendicular on QO. Okay, so here this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And we will define the touching point of the perpendicular from point P and QO as L. I'll repeat again, point L is the touching point of the perpendicular from point P and QO. Actually, by this construction, we created here quadrilateral PLOM and quadrilateral PLOM. This quadrilateral has 1, 2, 3 right angles. So I write it down. Quadrilateral LPOM has 3 right angles, and the sum of 3 right angles is 90 degrees times 3 is 270 degrees. So 270 degrees plus the size of this angle, that is actually angle LPM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? The sum of those 4 angles must be equal to 360 degrees. Here we subtract 270 degrees from this equation, and we will get that the missing angle LPM is equal to 360 degrees minus 270 degrees is 90 degrees. Okay, so I found out that angle LPM it is a right angle, it is equal to 90 degrees. So actually we found out that all the angles inside quadrilateral LPOM are right angles. Quadrilateral LPOM has 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral LPOM as a rectangle. I'll repeat again, because of the fact that quadrilateral LPOM has 4 right angles, we relate to quadrilateral LPOM as a rectangle. And you also know that the opposite sides of a rectangle are equal to each other. Okay, so the opposite sides of rectangle LPOM are equal to each other, that is to say, side PM must be equal to side AO. Side PM must be equal to side LO. In quadrilateral LPOM, side PM equals to LO according to the rule that the opposite sides of a rectangle are equal to each other. But we know that PM equals to 2, so we can write down that PM equals to 2. And for this equation 2 equals to PM equals to LO, we will derive that side LO is also equals to 2 units. Here side LO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that side LP equals to side OM. LP equals to OM. Side LP equals to side OM according to the rule that the opposite sides of a rectangle are equal to each other. So if we define side LP as X, here side LP equals to X according to our definition, side LP equals to X, then from this equation X equals to LP equals to OM, we will derive that side OM is also equals to X. Okay, side OM equals to X. In the next step, we'll focus at this point, that is the touching point of the circle and the quarter circle. And we'll define the touching point of the circle and the quarter circle as point K. I repeat again, point K is the touching point of the circle and the quarter circle. So actually at point K, the circle and the quarter circle have an internal lunge between them. That is to say, at point K, they are touching each other internally. And whenever you have two circular shapes that are touching each other internally, that have an internal lunge between them, then the straight line that joins their centers together must pass through their touching points. I'll repeat again. Whenever you have two circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass for their touching point, that is actually point K in this case. So here, point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that joins their centers together is the straight line OP. And that straight line OP that joins their centers together must pass for their touching point. That is to say, it must pass for point K, that is their touching point. So if the straight line OP must pass for point K, it means that OPK is one straight line. So I can write down that OPK is one straight line. Line segment OPK is one straight line. You can also say, in other words, that points O, P, and K they are all located on the same straight line. Okay, points O, P, and K they are all located on the same straight line. It is exactly like saying that OPK is one straight line. So if OPK is one straight line, it means that OK it is a straight line. OK is a straight line. OK is a straight line. So what is the definition of the straight line OK? Here, point O is the center of the quarter circle. Point K is the point of the quarter circle itself. This is exactly the definition of a radius. That is to say, OK is the radius of this quarter circle. OK is the radius of the quarter circle. Therefore, OK equals to capital R, because according to our definition, the radius of the quarter circle is defined as capital R. So OK equals to capital R. Likewise, point P is the center of the circle. Point K is the point of the circle itself. So this is exactly the definition of a radius. That is to say, line segment PK is the radius of this circle that is equal to 2 units. So PK equals to 2 units. So in conclusion, we found out that OK equals to capital R, it is the radius of the quarter circle, and PK equals to 2 units, it is the radius of the circle. And what is the length of line segment PO? The length of line segment PO equals to KO minus PK. I will write it down. The length of line segment PO equals to KO minus KP. I repeat again. PO equals to KO minus KP. Repeat again. The length of line segment PO equals to KO minus KP. So PO equals to KO. KO is the radius of the quarter circle that is equal to capital R. Minus PK. PK is the radius of the circle that is equal to 2. So in conclusion, we found out that the length of line segment PO equals to capital R minus 2. So I write it down here that PO equals to capital R minus 2. So in the next step, I will copy the right triangle POM in this new page, and we will implement the Pythagoras theorem on this right triangle POM. Okay, so here we already found out that the hypotenuse OP equals to capital R minus 2. The hypotenuse OP equals to capital R minus 2, OM equals to X, and PM equals to 2 units. It is the radius of the circle. So this is the right triangle OPM that I copied from the original drawing. In the next step, we will implement the Pythagoras theorem on this right triangle OPM. So I write down here, by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, therefore the square of the hypotenuse is OP squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM squared plus PM squared. Okay. So here OP equals to capital R minus 2, therefore OP squared equals to capital R minus 2 squared, and it is equal to OM squared. OM equals to X, so OM squared equals to X squared plus PM squared. PM equals to 2, therefore PM squared equals to 2 squared, that is 4. So in conclusion, found out that according to equation number 1, R minus 2 squared equals to X squared plus 4. Here we will open the brackets on this side of equation number 1, and we get that R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2 is minus 4R, and it is equal to X squared plus 4. So here we have 4 on both sides of equation number 1, so 4 will get cancelled. Okay, we get cancelled. And what is left from equation number 1 after we cancel 4? What is left? It's actually we have here, according to equation number 1, X squared equals to R squared minus 4R. Okay. So according to equation number 1, X squared equals to R squared minus 4R. In the next step, we will focus at this point. This point is the touching point between the circle and the semicircle. So we will define the touching point between the circle and the semicircle as point T. So at point T, the circle and the semicircle are touching each other externally. That is to say, at point T, the circle and the semicircle have an external arch between them. Okay? And whenever you have two circular shapes that have an internal and external notch between them, like in this drawing, those two circular shapes are touching each other externally. So whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. In this case, it is point T. I will repeat again. Whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point, that is actually point T. Okay, here the center of the circle is at this point P, the center of the semicircle is at point Q, and the straight line that joins their centers together is the straight line QP. And this straight line QP, must pass through their touching point, that is point T. The straight line QP that joins their centers together must pass through their touching point, that is point T. So if the straight line QP must pass through point T, it means that QTP is one straight line. So I write it down. QTP is one straight line. And in other words, you can also say that all the points Q, T, and P, they are all located on the same straight line. It is exactly like saying that QTP is one straight line. So if QTP is one straight line, it means that QP is also a straight line. QP is a straight line. And what is the length of the straight line QP? The length of the straight line QP, from the drawing it is very easy to see that QP equals to QT plus TP. I'll repeat again. The length of the straight line QP is equal to QT plus TP. Okay? So here point Q is the center of the semicircle. Point T is the point of the semicircle itself. Therefore QT is the radius of this semicircle, that is equal to 2 units according to what is given as the question. Likewise, point P is the center of the circle. Point T is the point of the circle itself. Therefore PT is the radius of this circle, that is also equals to 2 units. So in conclusion, we found out that QT equals to 2 and TP also equals to 2. So here we can write down that QT equals to 2 and TP also equals to 2. Therefore QP that is equals to QT plus TP equals to 2 plus 2, that is 4. So in conclusion, we found out that the length of the straight line QP equals to 4 units. Okay, we can write down here that QP or PQ, this is the same. It is equal to 4 units in its length. Okay. And what is the length of line segment AQ? Here, point Q is the center of the semicircle. Point A is the point of the semicircle itself. Therefore, AQ is the radius of this semicircle, that is equal to 2 units, according to what is given as the question. And what is the length of line segment QL? The length of line segment QL, it will be equal to AO minus AQ minus LO. So the length of line segment QL equals to AO minus AQ minus LO. I'll repeat again. The length of line segment QL equals to AO, that is actually the radius of the quarter circle, minus AQ, that is equal to 2 units, it is the radius of the semicircle, minus LO, that is equal to 2 units. So I'll write it down. QL equals to AO is the radius of the quarter circle, that is equal to capital R, minus AQ, it is the radius of the semicircle, that is equal to 2 units, minus LO, that is equal to 2 units. So in conclusion, I found out that QL equals to capital R minus 2 minus 2, minus 2 minus 2 is minus 4, so I found out that QL equals to capital R minus 4. Okay. Here QL equals to capital R minus 4. So in the next step, I will copy the right triangle QLP in a new page, and we will implement the Pythagoras theorem on this right triangle QLP. Okay, so here we just right now found out that QL equals to capital R minus 4. Side LP equals to X, and the hypotenuse QP, we've already found out that the length of the hypotenuse QP is 4 units. So this is the right triangle QLP that I copied from the original drawing. So in the next step, we will implement the Pythagoras theorem on this right triangle QLP. So I write down here that by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, therefore the square of the hypotenuse is QP squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to QL squared plus LP squared. Okay, so here QP equals to 4, therefore QP squared equals to 4 squared, that is 16. And it is equal to QL squared. QL equals to capital R minus 4, therefore QL squared equals to capital R minus 4 squared. So instead of capital R, I'll say R, okay? Plus LP squared. LP equals to X, therefore LP squared equals to X squared. So here we will open the brackets on this side of equation number 2, and we get that according to equation number 2, 16 equals to R minus 4 squared. R minus 4 squared equals to R squared plus 4 squared, it is 16. Minus 2 times R times 4 is minus 8R. plus x squared. So here we have 16 on both sides of the equation, so 16 will get cancelled. And what is left from equation number 2 after we cancel 16? In this side of the equation, nothing is left. We have 0, that is equal to r squared minus 8r plus x squared. Here we will add 8r to this equation, equation number 2, and we will get that according to equation number 2, 8r equals to r squared plus x squared. So here we will subtract r squared from this equation, equation number 2, and we get that according to equation number 2, eight r minus r squared equals to x squared. Okay, and we already found out that according to equation number 1, x squared equals to r squared minus 4r. So we actually have two different expressions for x squared. Now we create equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. X squared according to equation number 1 is r squared minus 4r, while x squared according to equation number 2 is 8r minus r squared, and those two expressions must be equal to each other. So here we will add r squared to this equation, equation number 3, and we will get that according to equation number 3, r squared plus r squared is 2r squared minus 4r squared minus 4r equals to 8r. According to equation number 3, here we will add 4r to this equation, equation number 3, and we get that according to equation number 3, 2r squared, 4r minus 4r is 0, and 8r plus 4r equals to 12r. So according to equation number 3, we found out that 2r squared equals to 12r. Here we will divide this equation, equation number 3 by 2, and we get that 2r squared over 2 is r squared. That is equal to 12 over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we subtract 6r from this equation, equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. So here we take r is a common factor from these two expressions. So r is a common factor. What is left from r squared after we took from it r is a common factor. What is left, it is actually r. And what is left from minus 6r after we took from it r is a common factor. What is left is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution is that r equals to 0, and the second solution is that r minus 6 equals to 0. So according to the first solution, r equals to 0. but because of the fact that r is the radius of this quarter circle, it must be a positive number. It can never be equal to 0, therefore we cancel the solution, and we left only with the second solution that r minus 6 equals to 0. Here we will add 6 to this equation, and we get that r equals to 6 units. So we found out that the radius of this quarter circle, it is equal to 6 units. Okay? Therefore, the area of this quarter circle will be equal to the area of the circle over 4. The area of the circle is pi r squared, and if you divide it by 4, we get the area of this quarter circle. So pi r squared over 4 is the area of this quarter circle, when r equals to 6. And what is the value of the shaded area? The value of this shaded area, it will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I repeat again, the value of the shaded area in the drawing equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Okay, so the value of the shaded area will be equal to the area of the quarter circle, and I've already explained that the area of the quarter circle equals to pi r squared over 4 when r equals to 6 units. Minus the area of the circle, the area of the circle is pi r squared when r equals to 2, therefore it is pi 2 squared. And the area of the semicircle equals to the area of the circle over 2. And the area of the circle is pi r squared and r equals to 2. So pi r squared over 2 is the area of the semicircle, and r equals to 2, so it is pi 2 squared over 2. In conclusion, we found out that the value of the shaded area equals to this expression. Here, we already found out that the radius of the quarter circle equals to 6, so r equals to 6, therefore r squared is 6 squared, that is 36. So in total, this expression equals to 36 pi over 4 minus pi 2 squared. 2 squared is 4, 4 times pi is 4 pi. So the area of the circle is 4 pi, minus the area of the semicircle, that is pi 2 squared over 2. 2 squared is 4, 4 over 2 is 2, and 2 times pi is 2 pi. So the area of the semicircle equals to 2 pi, and here we have 36 over 4 is 9, and 9 times pi is 9 pi, so in total this expression equals to 9 pi minus 4 pi, that is the area of the circle, minus 2 pi, that is the area of the semicircle. So in conclusion, we found out that the value of the shaded area equals to 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 2 pi. And this is 3 pi. Again, 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area is equal to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, I'll repeat again. The value of this shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. We finished with the second question. In the next step I will summarize the lecture. I will start with the first question. So in the drawing we have triangle ABC. Angle ABC equals to 30 degrees, angle ACB also equals to 30 degrees, and this angle TA equals to 60 degrees. Line segment BD equals to 5 units, line segment EC equals to 4 units, and our mission is to find out the length of line segment DE that is equal to X. So we focused on triangle ABC. In triangle ABC, those two angles are equal to each other, they are both equal to 30 degrees, therefore they are equal to each other. So here in triangle ABC, angle ABC equals to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in a triangle, there are equal sides, we get that in front of this angle we have side AB, in front of this angle we have side AC, and therefore side AB equals to side AC because of the fact that they are located in front of equal angles. So here side AB equals to side AC. Okay. In the next step, we defined angle BAD, this angle is alpha, and angle CAF, angle EAC is beta. And we know that the sum of the angles in any triangle is equal to 180 degrees, and especially in triangle ABC. So which angles we have in triangle ABC? We have this angle that is equal to 30 degrees, plus this angle that is also equal to 30 degrees, plus this angle that is equal to alpha, according to our definition, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta. In total, the sum of those all angles must be equal to 180 degrees. Okay? So here, this equation expresses the fact that the sum of the angles in triangle ABC equals to 180 degrees. So here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in this side of the equation, we have 120 degrees plus alpha plus beta. In the other side of the equation, we have 180 degrees, so it is equal to 180 degrees. So here we subtracted 120 degrees from this equation, and we found out that alpha plus beta equals to 180 degrees minus 60 degrees. It is 180 degrees minus 120 degrees. It is equal to 60 degrees. So we found out that alpha plus beta equals to 60 degrees. Then we did two constructions. In the first construction, from point A, we draw a straight line in such a way that the angle between the straight line and side AC equals to alpha. So this angle equals to alpha according to our construction. And the second construction that we did is from point C, we draw a straight line in such a way that the angle between the straight line and side CA equals to 30 degrees. So this angle equals to 30 degrees according to our construction. Then we extended the two straight lines until they intersect with each other at point F. Point F is the intersection point of the two extended straight lines that we constructed. Then we proved that the new triangle that we created here, triangle AFC, can go into this triangle, triangle ABD. So why those two triangles can go into each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So here angle BAD equals to angle CAF, they are both equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. So here, side AB equals to side AC. And finally, those two angles are both equal to 30 degrees, therefore they are equal to each other. So here, angle ABD equals to angle ABD equals to angle ACF, they are both equal to 30 degrees, therefore they are equal to each other. So actually, we have proved that this triangle ABD is congruent to this triangle AFC according to angle side angle rule. We have those two angles in the side that attach to those two angles in triangle ABD that corresponding congruent to those two angles in the side that attach to those two angles in triangle AFC. Therefore, those two triangles congruent to each other according to angle side angle rule. As from the fact that those two triangles congruent to each other, we will conclude that side BD equals to side FC. Yeah. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given us in the question, side BD equals to 5 units. So we can write here that BD equals to 5 units, and from this equation 5 equals to BD equals to FC, we will derive that FC also equals to 5 units. Here, FC also equals to 5 units. And the second thing that we conclude is that side AD equals to side AF. Yeah. Side AD equals to side AF according to the rule that corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, here AD equals to A according to our definition, here AD equals to A, then from this equation A equals to AD equals to AF, we will derive that side AF is also equals to A. Here side AF equals to A. Then we join points E and F together by a straight line, and we prove that the green triangle is congruent to the orange triangle. First of all, we have already found out that alpha plus beta equals to 60 degrees, so this angle, that is alpha plus beta, angle FAE, equals to 60 degrees according to what we have already found out. So why the green triangle is congruent to the orange triangle? First of all, we just write down proof that side AD equals to side AF. So AD equals to AF is equal to A. Both sides are equal to A, therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees, therefore they are equal to each other. Here, angle DAE equals to angle EAF. They are both equal to 60 degrees, therefore they are equal to each other. And finally, here, side AE is a common side that belongs to both triangles, so therefore side AE equals to itself. AE equals to AE is a common side that belongs to both triangles. So we actually proved that those two triangles can go into each other according to side angle side rule. I will explain what I mean. Those two sides and the angle that is included between those two sides in the green triangle are corresponding congruent to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that side DE equals to side EF. Here, side DE equals to side EF according to the same rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the question, side DE equals to x. So we can write here that DE equals to x, and from this equation x equals to DE equals to EF, we will derive that side EF is also equals to x. Here, side EF is also equals to x. In the next step, I presented to you the law of cosines, and we implemented the law of cosines in this triangle, triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle. So this triangle, triangle ABC, could be any triangle. And we know that side AB of triangle ABC equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, the following equation is true that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So then we implemented this law, the law of cosines, in triangle EFC. So I copied triangle EFC in this page, and we implemented the law of cosines in this triangle EFC. This angle ECF equals to 30 degrees plus 30 degrees, that is 60 degrees. Side EC equals to 4 units, side EF equals to 5 units, and side FE equals to X, that is the line segment that we are looking for, X. So in this triangle EFC, according to the law of cosines, we get that X squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I repeat again, X squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees according to the law of cosines. So here we have X squared that is equal to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 14, times cosine 60 degrees. Cosine 60 degrees is 1 half, so we substituted cosine 60 degrees by 1 half, so in conclusion, in total, this expression equals to minus 40 times 1 half. So we have here X squared that is equal to 60 plus 25 is 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that X squared equals to 41 minus 20. So X squared equals to 41 minus 20 is 21. So X squared equals to 21. We took out of this equation and found out that X equals to either to the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. And the reason that we took the positive square root of 21 is because of the fact that X is a length. X as a length, it must be a positive number. So we found out in conclusion, found out that the length of line segment DE that is equal to X equals to either to the positive square root of 21, in terms of numbers, it is equal to 4.58 units. We finished the first question. Then I presented to you the second question. So, in the drawing, we have a quarter circle. Inside this quarter circle, we have a semicircle and the circle that are tangent to each other at point T. And we also know that this circle is tangent to the quarter circle at point K. And we know that the radius of the circle is equal to 2 units, and the radius of the semicircle is also equal to 2 units. And our mission is to find out the value of the shaded area. Okay, so first of all, because of the fact that this is a quarter circle, point O must be the center of the quarter circle. Angle LOM, this angle must be equal to 90 degrees, and line segment OB and line segment AO, they are both must be the radii of this quarter circle. So we define the radius of the quarter circle as capital R, therefore AO equals to capital R, and OB is also equals to capital R. They are both the radii of the quarter circle. Okay, in the next step, here we have the radius OB that is tangent to this circle at point M. Point M is the point of tendency of tangent OB with this circle. Here point P is the center of the circle. Point M is the point of the circle itself, therefore PM is the radius of this circle that is equal to 2 units. We also define the center of this semicircle as point Q. Here we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have tangent AB that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius of M that is drawn to the point of tendency, and whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, which means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule number 1. So we actually implemented rule number 1 in our drawing. In our drawing, we have the radius PM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent OB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MP. So if OB is perpendicular to MP, it means that this angle equals 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then from the center of this circle, that is to say from point P, we draw perpendicular on QO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And we define the touching point of the perpendicular from point P and QO as L. So here, by doing this construction, actually we created here quadrilateral LPOM that has 1, 2, 3 right angles. Again, this quadrilateral LPOM has 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle LPM. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation, and found out that the missing angle NPM equals to 360 degrees from 270 degrees, it is equal to 90 degrees. Okay, so the missing angle, this angle, it is a right angle, it is equal to 90 degrees. So we actually found out that inside quadrilateral LPOM, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we related to quadrilateral LPOM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, rectangle LPOM, side PM must be equal to side LO. PM equals to LO, according to the rule that the opposite sides of a rectangle are equal to each other. But PM equals to 2, so we can write here that PM equals to 2, and from this equation 2 equals to PM equals to LO, we will derive that side LO also equals to 2 units. Likewise, according to the same rule, side LP must be equal to side OM. Side LP must be equal to side OM, according to the rule that corresponding sides in congruent triangles are equal to each other. So if we define side LP as x, here side LP equals to x, well, from this equation x equals to LP equals to OM, we will derive that OM is also equals to x. Here OM is also equals to x. In the next step, we focus at this point, point K, that is the touching point of the circle and the quarter circle. At point K, the circle and the quarter circle have an internal notch between them. That is to say, they are touching each other internally at point K. And whenever you have two circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass for their touching point. In this case, it is point K. I'll repeat again, whenever you have two circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass for their touching point. In this case, it is point K. So here, point O is the center of the quarter circle. Point P is the center of the circle, and the straight line that joins the centers together is the straight line PO. And according to the rule that I mentioned, the straight line PO must pass from point K, that is their touching point. Or in other words, if the straight line OP must pass through point Q, it means that OPK is one straight line. Okay, so we can write down that OPK is one straight line, or we can also say in other words that points O, P, and K, they are all located on the same straight line. Okay, so if OPK is one straight line, then OK is also a straight line. Okay, is a straight line. And what is the definition of the straight line OK? Point O is the center of the quarter circle. Point K is the point of the quarter circle itself. This is exactly the definition of radius. That is to say, OK is the radius of this quarter circle that is equal to capital R. Here, OK is the radius of the quarter circle that is equal to capital R. Likewise, so the third OK is the radius of the quarter circle. So here point P is the center of the circle. Point K is the point of the circle itself. Therefore, PK is the radius of this circle that is equal to 2 units according to what is given as the question. So in conclusion, we found out that OK equals to capital R, it is the radius of the quarter circle, and PK equals to 2 units, it is the radius of the circle. And what is the length of line segment PO? The length of line segment PO equals to KO minus KP. Again, KO minus KP equals to PO. I repeat again, PO equals to KO minus KP. We have already found out that KO equals to capital R, and PK or KP equals to 2, therefore PO equals to capital R minus 2. Okay, so here I copied the right triangle POM in this new page and we implemented the Pythagoras theorem on this right triangle, triangle POM. We have already found out that PO, the hypotenuse PO equals to capital R minus 2. Here PM equals to 2 units, this is the radius of the circle, and OM equals to X. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is OP square, it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to OM square plus PM square. So OP equals to capital R minus 2, therefore OP square equals to capital R minus 2, and it is equal to OM square, OM equals to X, so OM square equals to X square, plus PM square. PM equals to 2, so PM square equals to 2 square, that is 4. So in conclusion, according to equation number 1, we found out that R minus 2 square equals to X square plus 4. Here we open the brackets on this side of equation number 1, and we found out that R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2, that is minus 4R, and it is equal to X square plus 4. So here we have 4 on both sides of the equation, so 4 will get cancelled. And what is left from equation number 1 after we cancelled 4? What is left? Here we have X square that is equal to R square minus 4R. I repeat again that according to equation number 1, we found out that X square equals to R square minus 4R. Then we focused at this point. This point is the touching point of the semicircle and the circle itself. So we defined the touching point of the circle and the semicircle as point T. Actually, at point T, the circle and the semicircle have an external notch between them. I repeat again, at point T, the circle and the semicircle have an external notch between them. And whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. I repeat again, whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. In this case, it is point T. So here, point P is the center of the circle. Point Q is the center of the semicircle, and the straight line that joins their centers together is the straight line QP. And that straight line QP must pass for their touching point, that is point T. So if the straight line QP must pass for point T, it means that QTP is one straight line. Okay? So QTP is one straight line. Or we can also say, in other words, that points Q, T, and P, they are all located on the same straight line. So if QTP is a straight line, it means that QP is also a straight line. Okay, QP is a straight line, and what is the length of the straight line QP? The length of the straight line QP, it is very easy to see from the drawing that the length of the straight line QP is equal to QT plus TP. Again, QP equals to QT plus TP. What is the length of QT? Here, point Q is the center of the semicircle. Point T is the point on the semicircle itself. That is to say, QT is the radius of this semicircle that is equal to 2 units according to what is given as the question. Likewise, here, point P is the center of the circle. Point T is the point on the circle itself. Therefore, TP is the radius of this circle that is also equal to 2 units. So in conclusion, we found out that QT equals to 2 and TP also equals to 2. Therefore, QP that is equal to QT plus TP equals to 2 plus 2. That is 4. So we found out that QP, the straight line QP equals to 4 units. Then we found out the length of line segment AQ. Point Q is the center of the semicircle. Point A is the point of the semicircle itself. Therefore, AQ is the radius of this semicircle that is equal to 2 units, according to what is given as the question. Okay, then we found out the length of line segment QL. What is the length of line segment QL? It is very easy to see from the drawing that QL equals to AO minus AQ minus LQ. Again, QL equals to AO minus AQ minus LO. Okay, so repeat again, QL equals to AO minus AQ minus LO. AO equals to the radius of the quarter circle, that is equal to capital R. AQ equals to 2 units, this is the radius of the semicircle. And LO equals to 2 units. So in conclusion, we found out that QL equals to capital R minus 2 minus 2. Minus 2 minus 2 is minus 4. Therefore, we found out in conclusion that QL equals to capital R minus 4. Here, QL equals to capital R minus 4. Then I copied the right triangle QLP here in this page. And we implemented the Pythagoras theorem on this right triangle QLP. Okay, this is the right triangle QLP. This is the right triangle QLP that I copied from this new page, and we implemented the Pythagoras theorem on this right triangle QLP. We just right now found out that QL equals to capital R minus 4. The hypotenuse QP, we already found out that the hypotenuse QP equals to 4 units, and LP equals to X. So we implemented the Pythagoras theorem on this right triangle QLP. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, therefore the square of the hypotenuse is QP squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to QL squared plus LP squared. So according to the Pythagoras theorem, QP squared equals to QL squared plus LP squared. This is equation number 2. So QP equals to 4, therefore QP squared is 4 squared, it is 16. And it is equal to QL squared. QL equals to capital R minus 4, therefore QL squared equals to capital R minus 4 is minus capital R minus 4 squared. LP equals to X, therefore LP squared equals to X squared. So in conclusion, we found out that according to equation number 2, 16 equals to capital R minus 4 squared plus X squared. Here instead of capital R, we say R, because we have only one area. So 16 equals to r minus 4 squared plus x squared. So here we open the brackets on this side of the equation and we found out that 16 equals to r minus 4 squared plus x squared. So r minus 4 squared equals to r squared plus 4 squared, that is 16, minus 2 times r times 4, that is minus 8r, plus x squared. So we have 16 on both sides of the equation, so 16 will get cancelled. What is left from equation number 2 after we cancel 16? In this side of the equation nothing is left, we have 0. In the other side of the equation we have r squared minus 8r plus x squared. Here we added 8r to this equation, equation number 2, and we found out that 0 plus 8r is 8r, and it is equal to r squared plus x squared. Here we subtracted r squared from this equation, equation number 2, and we found out that according to equation number 2, 8r minus r squared equals to x squared. Okay, so according to equation number 2, x squared equals to 8r minus r squared. Here, so according to equation number 2, x squared equals to r squared minus 4r, and according to equation number 1, actually according to equation number 2, x squared equals to 8r minus r squared, while according to equation number 1, we found out that x squared equals to r squared minus 4r. Therefore, we created equation number 3 that states that, so we have two different expressions for x squared. Therefore, we created equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So x squared according to equation number 1 is r squared minus 4r, and it must be equal to x squared according to equation number 2, that is 8r minus r squared. And so here we added r squared to this equation number 3, and we found out that r squared plus r squared is 2r squared minus 4r equals to 8r. Here we added 4r to this equation number 3, and we found out that 2r squared 4r minus 4r is 0, and it is equal to 8r plus 4r, that is 12r. So in conclusion, we found out that according to equation number 3, 2r squared equals to 12r. Here we divided this equation number 3 by 2, and we found out that 2r squared over 2 is r squared, and 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we subtracted 6r from this equation number 3, and we found out that r squared minus 6r equals to 0. Okay, so here we took r as a common factor out of those two expressions, so r is a common factor. What is left from r squared after we took from it r as a common factor? What is left is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. Either r equals to 0 or r minus 6 equals to 0. So according to the first solution for r equals to 0. But because of the fact that r is the radius of this quarter circle, r is a length. So r as a length, it can never be equal to 0. It must be a positive number. So we cancel this solution, r equals to 0, and we left only with the second solution that r minus 6 equals to 0. Here we added 6 to this equation, and we get that r equals to 6. So in conclusion, we found out that the radius of this quarter circle is equal to 6 units. Therefore, the area of the quarter circle will be equal to the area of the circle, that is pi r squared over 4, and r equals to 6. And what is the value of the shaded area? The value of the shaded area will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Repeat again, the value of the shaded area will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. We have already found out that the area of the quarter circle equals to pi r squared over 4 when r equals to 6. The area of the circle is pi r squared and r equals to 2, so it is pi 2 squared. And the area of the semicircle equals to the area of the circle over 2. So the area of the circle is pi r squared and r equals to 2. So it is pi 2 squared over 2. This is the area of the semicircle. So here, the area of the quarter circle r equals to 6. Therefore, r squared is 6 squared, that is 36. So in total, this expression equals to 36 pi over 4. That is the area of the quarter circle. Minus the area of the circle, that is pi 2 squared. 2 squared is 4, and 4 times pi is 4 pi, that is the area of the circle. Minus the area of the semicircle, that is pi 2 squared over 2. 2 squared is 4, 4 over 2 is 2, 2 times pi is 2 pi. So in conclusion, the area of the semicircle is 2 pi. Here, 36 over 4 is 9, so in total this expression equals to 9 pi, that is the area of the quarter circle, minus the area of the circle, that is 4 pi, minus the area of the semicircle, that is 2 pi. So 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 units. I repeat again, the value of this shaded area will be equal to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay? Thank you very much.